In the last class, we started discussing extensively about total correlation spectroscopy called Toxy. Again, it gives you correlation information among the coupled partners of a given spin system. This is an extended version of the COSY, where there is a relay transfer of the magnetization from one spin to another spin like that from the group of coupled spins, so long as they form there is a coupling among them and forms a coupled spin system. I also told you how it works. It works because during the spin lock pulse which we are going to apply, then what is going to happen is the chemical shift differences become 0, and then there exists a J coupling, because the spin lock pulse can be treated as if it is like an infinite number of spin-across sequences which are closely spaced. As a consequence, chemical shift evolution is not there, whereas J couplings do evolve. So it creates a strong coupling spin system, in which case spins can exchange energy among its coupled partners. And there is a cyclic exchange of energy. It will go from one to other one depending upon the mixing time you are going to give, and also depending upon the coupling strength I said. It keeps going among all the coupled partners, and then if you extend for a long time, it may even come back. There is always going on cyclic exchange. It doesn't go unidirectionally. It gives you next spin, come back. At the same time, it will be coming back from the next spin. Go to the third spin, again it is coming back. So the cyclic phenomenon is going on. So we understood how a Toxy works. It is much better than a COSY. In one experiment, all the coupled partners can be identified, whether they come vertically or go horizontally from the diagonal peak. All the cross peaks identifies the coupled partners. So that's what we understood, and we took one or two examples and compared that with the COSY spectrum, how it is advantageous, and where in the COSY we have to go in a stepwise manner. That's what we discussed. We will go further today with one or two more examples and discuss more about Toxy, advantage of Toxy. Okay, so this is another example of a 500 MHz 1s NMR spectrum of isovaleryrate in chloroform, and this is the spectrum. Of course, analysis of the spectrum is not difficult at all. If you carefully see which are the peaks, how do you analyze everything, we know it. But let us not get into the 1D analysis of this. We will straight away see how we can analyze this in an easy way. By using Toxy, we can assign the peaks in one shot. And of course, looking at the molecule, you can identify there are only two groups of coupled spins here. This CH3, CH2, 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 1 to 3, 4 form one coupled spin system, and 6 to 9 forms another coupled spin system. If you do a COSY, there is a breakage, because you can go from 1 to 2, 3 to 3 to 4 like that. And again you have to identify another peak from the diagonal, start with 6, 7, 8, 9, you go systematically. But a simple Toxy spectrum of this molecule is like this. You start with one of the peak, any peak, horizontally or vertically I told you. You can see from this diagonal, you come horizontally, you get 4 peaks. And I will say this peak, and this peak. If you go vertically, this one, and this one. They are all coupled partners. That forms a spin system. And you can get this. This is H1, 2, 3, 4. I started with one of them. This was H4 identified because it is attached to C double bond O. So there is a confidence in the assignment. Using that as peak on the diagonal, we went horizontally and identified all the peaks. Of course, you can go vertically also. As I told you, you can identify all the same 4 peaks. Okay. So if you go vertically, you can go back here and identify the coupled partners very easily. So this is one spin system. Go further, you can see there are 4 peaks here. Start with this diagonal, come here 1, 2, 3, 4. So you can identify all these 4 coupled partners. See, started with this proton, which is 6, which is attached to oxygen, and then it comes to here, here, and here. Everything can be easily identified. Of course, so one of them, of course, has a very weak kineticity. As I told you, it depends upon the coupling strength and the mixing time. Okay. Another spin system is identified. So it is easily Toxy identified 2 spin systems. Now we will start with the analysis of the 2D Toxy spectrum of beta-2-glucose in CDCl3. This is a molecule. It is a disaccharide. Okay. Let us see how we analyze this disaccharide. It has a glycosidic linkage also. But there are 8 acetyl esters here. Each of them consisting of 1, 2, 3, 4, 5, 6, 4, 6, etc. in the beta lactose. You can see which are those acetyl esters like these 4 and these 4. These are the 8 acetyl esters which are present. And each saccharide has 7 chemically inequivalent protons. Here, here. I have marked 6, but remember H6 has 6 and 6 prime both. All others have single protons, but other one 6 has 2 protons. So there are 7 chemically inequivalent protons here in each of the ring, each of the saccharide group. Okay. So we have 2 coupled spins. Definitely we should identify, because we analyzed the glucose spectrum of the COSY and earlier a few examples. We always start with an anomeric proton and then we could identify all the coupled partners. Here also we should do that. But we can also, instead of doing through COSY, we can also do through the Toxy. This is one coupled spin system, this is another coupled spin system. We will do the Toxy. Okay. Now, Toxy should exhibit correlation among all the coupled protons, of course depending upon the mixing time, because it's a big system. From one proton to all the 6 protons, if it has to go, we have to have mixing time quite large. Because remember, mixing time will be of the order of milliseconds here, 30 milliseconds, 50 milliseconds, up to sometimes 80 milliseconds we can go, 100 milliseconds like that. Large mixing time becomes larger. But you can't give enormously. If you give more than whatever is required, more 200, 300 like that, whatever the gain you lost, your gain will be losing, because the magnetism again comes back to the starting spin. This is what happens. This is the toxic spectrum of this beta D glucose with a mixing time of 70 milliseconds. Mixing time is of the order of several milliseconds, I told you. Now, can you identify 2 coupled spin systems? Very easily we can identify. Start with any one of the row, that horizontal row. This corresponds to spin system A. You can identify 7 chemically inequivalent groups, I told you, 1, 2, 3, 4, 5, 6, 7. So this, and there is an overlap here, and there is an overlap here, this one, and this one, and this one. See, in a coupled spin system, there is a severe overlap. Just going horizontally, one row, you will identify all the coupled spin. Of course, everything remains identical. You can go to any row because it's symmetric. Everything you can go horizontally, vertically, column wise or row wise, you can identify all the spin system. Go to the other one, it identify another spin system. But you may see all the 7 peaks may not be seen there in the other one. You see, there are some issues. That is because beyond a certain level, magnetization transfer may be not become efficient, because the coupling between one of them become very weak. So, and there is a stop there. It reaches a dead end. But then don't stop at that. You can look for other rows. You can combine 1 or 2 rows if there is enough transfer of magnetization is not there among all the coupled spins because of weak coupling also in between. But you can use 2 or 3 rows and then get the required information. Like this you can do. This is one column, other column. That way identified all the, see here in this row, only 4 are identified. For the remaining 3, you can go like this. It's possible, right? So we can go like that and identify everything. And some of the toxic transfer peaks are barely visible. A simple doublet, you start with this thing that corresponds to anomeric proton, and of course with that we can draw the line and analyze everything. Only second spin system has a bottleneck, I told you. We are seeing only 4 because it doesn't go through the entire spin system. It is because bottleneck is at the proton C4 in the galaxy there is less coupling. There is equatorial axial coupling which is smaller. As a consequence, beyond that, Toxy doesn't transfer the magnetization to spin system. Very weak coupling. As a consequence, it may not have, but you can find out from the other one also, other preet. There are several rows. In some rows we can use, we can identify all the spin system and then assign all the peaks. Of course, you do the same thing in the COSY. You look at the advantage of Toxy and COSY. COSY, if you start like this and goes, you identify one spin system. Start with this one, okay, and I will go like this. 1, it will come to 2. I can identify 2, 2 to 3, identify 3, 3 to 4, and then 4 to 5 there, 4 and 5 are identified, and 5 to 6 here. 6 and 6 prime, 6A, both are there, 6A and B. Whole spin system you can identify. Here there is no bottleneck, even for the other one also. Other spin system also, you can keep going like this. All 6 you can identify. The advantage here, you can do it in a better way, but only step by step. In the Toxy, there are some issues where there is no complete transfer of magnetization, but of course you can combine both of them and analyze this one. Okay, where do you use this Toxy? Very efficiently, if you want to use the Toxy, think of a situation. Let us say you are working on a biomolecule like a peptide or a protein. What do these contain? What is the primary structure? They are consisting of amino acids of the primary structure, several sequence of amino acids, and each amino acid forms a spin system. For example, take glycine here, starting from NH3CH, COH, CH, this forms one spin system. Go to alanine, starting from CH3, CH, NH3 form one spin system, and go for the leucine, CH3, CH, CH2, CH, and NH3. All of them form a coupled spin system. So in each amino acid forms a coupled spin system. So there is a Toxy transfer of magnetization among all the protons right from CH3 to NH group. So what we will do, if there is a protein or a peptide you are analyzing, sequence of amino acids are there, simply draw a number of vertical lines, each of them will identify how many amino acids are there. And of course further you can interpret the spectrum very easily. So each amino acid forms a spin system and they are identifiable by one vertical row or horizontal row. That's what it is. Vertical line or horizontal line you draw and identify everything. This is the glycine, you see, start with CH, C alpha, come here, and then NH. Similarly for alanine, CH3 to C alpha and then NH. This is COSY, but Toxy identified in one row. Same way here, in the case of leucine, start with CH3, then it comes here to, and then here you have to come like this for COSY, step by step manner. Instead of that, what we do here is in one shot, CH3 to NH proton, all of them assigned in one shot. Otherwise we go here, NH to here, here like that. Several steps you have to do in COSY. But Toxy, you see, from CH3 to NH, all the coupled peak partners give rise to cross peaks. Any row you take, doesn't matter. Similarly, an example of Toxy of cysteine, glutamate, and some cases you can have 2 or 3 spin systems present. For example, in this molecule, if you consider tryptophan, this forms one spin system, this forms another spin system. So there will be 2 sets of peak like we saw in the previous example. So you can have 2 different spin systems to identify, you can identify everything. So you can see the advantage of the Toxy. It is in biomolecule, especially when you want to analyze bigger molecules like peptides or protein, Toxy is very, very useful to make the assignment. COSY is going to be very cumbersome there. You can use Toxy. Okay, like this. Oh yes, look at this leucine. Starting from NH3, completely everything has been taken. And methionine, starting from CH3 here up to NH, all the peaks can be identified. Okay. Now I will tell you one advantage of Toxy over COSY. What is an advantage? That is very interesting. Let us understand that. Where do you find it? Of course, already I showed the advantage. If you want to analyze a biomolecule like proteins or nucleic acids, nucleotides, if there are several, if a big saccharide if you consider, or a big protein, there is a limit of course to get the size of the protein. Then doing a Toxy helps you in identifying each amino acid by a single row or a single column. Fine. Apart from that, there are certain advantages. One of the advantages I am going to tell you now. Consider a situation, we have one spin system like this. There are 5 protons coupled. This is one coupling 1, 2, 1, 2, 3, 3, 4 and 4, 5. There are 5 different couplings for one spin system. Go to another spin system, same 5 protons. This I am going to call it as A, B, C, D, E. We have JAB, JBC, JCD, JDE. 2 different spin systems and it is mixed. You are going to run a Toxy. It so happens when you look at the spectrum, this chemical shift of 3 and chemical shift of 3 are overlapped, indistinguishable. Both of them come at the same chemical shift. What do you do now? Is there a problem in this analysis? Of course, there is a problem in the analysis if you are not careful. Look at this one, spin system. I can come here and then go. We will look at the COSY spectrum of this, where you get into problems. And this is the one spin system, 1, 2, 3, 4, 5. Other is other one. Now, how do you make the assignment? Start on the diagonal of one of them, 1 to 2, you go. Then 2 to 3, you go to 3 to 4, 4 to 5, perfect. You can analyze. Other one, start with E to B, D to C, B, A. Both the spin systems are clearly analyzed, identified. There is no problem at all. If my assignment is correct, in spite of the fact both are overlapped, both 3 and C are overlapped there, same chemical shift here. Accidentally it was right, but I can also make a mistake like this. Look at this. I can start with 1 to 2, 2 to 3, I will go. Here there is a overlap of 3 and C from 2 different spins, same chemical shift, both the peaks are coming. Now where do you go? This is also possible. Instead of going here to complete this, if I complete the analysis like this, you are right. Accidentally I showed you it is possible in the previous slide. But there is also a possibility you can go like this. You crossed over from one spin system to another spin system, 2 different molecules. You can make a mistake. Or you can also do like this. It is quite likely you can start with this. Now instead of going to red, I can go through blue. What happened? Here again I crossed over. When there is a overlap, when I am analyzing the COSY spectrum, there is every possibility that I can make a mistake if there is overlap. If they are completely overlapped and it is difficult for you to distinguish, we can make a mistake like this. We can cross over to the different spin system while analyzing. Alternately, what we can do is, I will run a Toxy. What does Toxy give? Toxy gives cross peaks among all the, for example, you take the blue spin, start from here, go like this, all the peaks you can identify, come like this, all the peaks you can identify. Similarly for the C, this one you can identify, all the 5 peaks. Even though there is a overlap here, you can distinguish them, which is not possible in the COSY. There is possibility one can make a mistake and cross over to a different spin system. You see the advantage of it. So Toxy has a better advantage at times when there is a severe overlap of the peaks. Simply Toxy you can do and then identify all the spin systems like this. So this is what I just wanted to tell you about Toxy. I showed you what is a Toxy, where do we use, and advantage of Toxy over COSY, etc. These are all both are homonuclear correlation experiments. With this, we will now switch over to a different topic, that is heteronuclear correlation experiment. I will start it right now. Okay, we will start with the heteronuclear correlation experiment. Okay. So far we discussed about homonuclear. Now we will switch over to entirely a different experiment where we are not correlating the same spins, we are correlating unlike spins, different spins, not like spins. We will start with this one. What it does, earlier case it was correlation from proton to proton, whether it is COSY or Toxy, does not matter. But here correlation is from proton to carbon or nitrogen or any other nuclei apart from the same spin. See, it will always have different heteronuclear correlation. What is the requirement for this? Again, there must be a J coupling. Using J coupling only, we can do the correlation. For all these correlation experiments, whether it is homonuclear, heteronuclear, J coupling is essential. In the homonuclear case, COSY and Toxy, coupling among protons, among homonuclear spins are needed. But here, coupling among heteronuclear spins are needed. That is what it is. And you can do the chemical shift connectivity between carbon 13 proton, nitrogen 15 proton, fluorine proton, etc. Any heteronuclear can be correlated. Usually, one of them is the abundant spin, other is the rare spin. You may ask me, what about the correlation among dilute spins? That is a different thing. I will come to that later. Okay. So, heteronuclear correlation experiment if I do, few important points you must remember. They are not symmetrical, unlike COSY and Toxy. Why? because in both the dimensions the chemical shift range is identical. If I am doing protons, so homonuclear COSY of protons, it is 10 ppm chemical shift range along F1 and 10 in the F2, identical. It forms a symmetrical thing, and there will be a diagonal. So with respect to diagonal, they are all symmetric. No doubt about it, that's true. But here they are not symmetrical because heteronuclear chemical shift ranges are different. Proton may go from 0 to 10 ppm, carbon 13 may go to 0 to 300 ppm. It is not square at all. So question of symmetry doesn't come at all. Chemical shift ranges are entirely different. So heteronuclear spectrum, first thing is not symmetrical, and there are no diagonal peaks here, okay, because in the homonuclear case in COSY both the dimensions are determining the same spin. For example, the proton is having a frequency, some frequency in T1 period. You are detecting the same thing, supposing if it remains unchanged, same frequency is retained in the T2 dimension also, you are going to get a diagonal peak because we are detecting both proton in both the dimensions. But in the second dimension here I am not detecting proton. So the question of diagonal does not come at all. There are no diagonal peaks in the heteronuclear correlation. And normally what we do is, the indirect dimension is less abundant spin. What do you mean by that? In the case of a 2D, this is direct dimension F2, this is F1, indirect dimension. Indirect dimension we always take less abundant spin like carbon 13, nitrogen 15, etc. Abundant spin is here proton, fluorine, etc. That is a convention. Indirect, of course you can do the reverse also. There is also possible nowadays, so many experiments are possible. We can even do indirect dimension abundant spin and direct dimension less abundant spin. Both are possible, inverse experiments is possible. But this was the convention for HETCOR. The indirect dimension less abundant, direct dimension abundant spin. Okay, what is the simplest HETCOR pulse sequence? It is like this. Heteronuclear pulse sequence is very simple. On the carbon 13 channel you have a detecting pulse, 90 pulse. In the proton channel you apply a 90-degree pulse and allow it to evolve for a time T1, that is a T1 period, evolution period. Then after that you give some delay, that where you apply inept mixing to do the polarization transfer. And then 290-degree pulses there. What it 290-degree pulses will do? I already explained to you. It will ensure that antiphase magnetization gets transferred from one spin to other spin. From proton to carbon, it can be transferred. So this is how, very simple pulse sequence. 290-degree pulses on the proton channel, T1 period evolution, but after the evolution there is inept mixing for polarization transfer. How this pulse sequence works, without going into the detail, I will explain to you. What does my first 90-degree pulse do? It will bring the magnetization to XY plane. That is what it does. And here magnetization starts evolving because I have applied 90-degree pulse. Then what does evolve? Carbon 13 chemical shift will not come here because I am applying pulse only in proton. So proton chemical shifts and proton chemical shifts start evolving here. Alright. And after some time, what I am going to do is, after the T1 period, I am going to do the inept here. What does inept does? It converts proton magnetization into antiphase with respect to carbon 13 for polarization transfer. We have understood what is inept. We discussed extensively for 2 or 3 classes. So inept creates antiphase magnetization of the proton with respect to carbon 13. Now simultaneous application of 290-degree pulses, what it will do? It will transfer the proton magnetization to carbon 13. So that means antiphase magnetization gets jumping. It jumps from proton to carbon and then start detecting the carbon 13 signal. That is what basically you do. Carbon 13 signal is detected, bring the magnetization to XY plane, allow it to evolve, do an inept for magnetization transfer, create antiphase magnetization of proton, applies 2 simultaneous 90-degree pulses, transfer to carbon 13 and start detecting the signal. This is the basic simple experiment. So in HETCOR, if you want to understand in brief, it gives information about which carbon is attached to which proton. It is done by inverting the proton population and varying the transfer of proton magnetization during T1. T1 when I vary this one, I will first bring down the magnetization and then of the proton that population and keep on varying the T1 period. Okay, that is how the two-dimensional way it is going to be done, and vary the transfer of polarization to carbon to 13 as a function of T1, and this depends upon JCH we use. You can have HETCOR experiment both decoupled version and coupled version. What is meant by decoupled version? I can see the carbon 13 with proton decoupling in the decoupling channel. I can use the carbon 13 channel, I can decouple proton, or I can see proton with carbon 13 decoupling. That is also possible. Both are possible. Or I can don't do decouple at all on both the dimensions, and both the dimensions I am going to get the coupled spectrum. So this is what happens, and this is the spectrum of HETCOR spectrum decoupled in both the dimensions. When you decouple in both the dimensions, interpretation of the HETCOR spectrum is fairly simple. You don't need to break your head at all. Very simple way to analyze. First of all, these are the protons peaks here. In this dimension, proton, and this dimension, it is carbon 13. Okay. In the proton, somehow we have said this to be CH3. Proton assessment has been done either by 1D way or the COSY, whatever the experiment you have done. This is another CH3, this and then this CH3, and then we have a CH2, CH2. Okay, all the three are there. Everything has been easily identified. This CH and CH3, CH3, CH2. There are two CHs, one CH3 and two CH3 and one CH2. Okay, this is what way it is. When I make the assignment, I know the proton chemical. If I get a peak in the HETCOR, heteronuclear correlation, sit on that peak, go horizontally. You see, hit the proton. In the proton dimension, I get proton chemical shift. Go vertically up, you get carbon 13 chemical shift. Very easy. So it correlates proton and carbon in this experiment. It is a proton carbon HSQC, heteronuclear correlation. I can correlate the chemical shift of two coupled nuclei, one bond directly attached. Which carbon is attached to which proton, I can find out. So this is what I told you. Remember, I was telling you when I was discussing in the introduction to 2D, simultaneous detection of two nuclei is not possible in 1D. That was a limitation. But now it is possible. Look at it. I get a peak. Simultaneously, I can get proton and carbon chemical shifts. If I do the coupled experiment, I can get heteronuclear coupling and also homonuclear coupling both, depending upon the type of experiment I do. So in one experiment, both the nuclei can be detected. That was the limitation of 1D. So I showed you the advantage of a 2D, especially in the HSQC. I can correlate. Like for example, come with this peak. Now go horizontally. It will identify this proton CH3 peak. Go vertically, I get the carbon 13 peak. Similarly for this. Very easily, you have to draw horizontal line and vertical line. Horizontally, if you come to proton axis, you get proton chemical shift, and this peak tells me CH chemical shift of proton and also carbon 13 chemical shift of the same CH group. This CH has carbon and proton. Its carbon chemical shift is this and proton chemical shift is this. For this proton, this is the proton chemical shift and this is the carbon chemical shift of the CH3 group. CH2 group. So very easily you can identify, don't get confused. Take the CH2 group. In the CH2 group, I go vertically, I get carbon chemical shift. Come horizontally, I get proton chemical shift. Here it is taken, this is carbon 13 axis, this is proton axis. It can be reversed depending upon the type of experiment you have done. You can identify chemical shifts in either dimension. Go vertically and horizontally, you can get the correlation information, heteronuclear correlation. Advantage also I can tell you. Take an example of molecule ipsenol. You can identify proton 1, CH3. This is the proton, the carbon dimension. This is proton chemical shift. Okay, that is the proton chemical shift. And vertically, if you go, you get carbon chemical shift. Similarly, for 2, they are overlapped. You can find out. You see this one. For the proton 3, you get carbon chemical shift and proton chemical shift. Look at this one, this proton 6, this is an advantage. This has two different chemically inequivalent protons. Like we saw in the glucose, 6 and 6 prime, they have different chemical shapes of proton, but same carbon attached to same carbon. Similarly here, these are two chemically inequivalent protons attached to same carbon. Now if I go vertically up here, I get the carbon chemical shifts, and then go horizontally, I get two different chemical shifts. One chemical shift of the one proton here, other chemical shift here for other proton. So this is an advantage. So into one this thing, one cross peak of the carbon correlates to two proton chemical shifts like this. So you can find out this thing. You look at this one also. This carbon 10 again has two protons. All of them very easily you can identify. So all you have to do HETCOR interpretation is very simple. Go horizontally or vertically, get proton chemical shifts and carbon chemical shift. If two different chemically equivalent protons are attached to same carbon, you will get the same one chemical shift in the carbon 13 dimension for the same carbon, but you have two different proton chemical shifts. So this is an advantage. So very easily you can do the experiment and do the interpretation like this. Okay. So now since the time is getting up, what I am going to do is, we have to extend this for the inverse spectroscopy. HSQC can be done in the heteronuclear correlation can be done in a different way. I am going to discuss that one in the next class. But what we discussed today, we discussed more about the Toxy, a few more examples. I showed you what is the advantage of Toxy over COSY. Toxy easily identify all the coupled spins in a spin system in one single experiment. Either you go vertically, draw a vertical line or a horizontal line from the diagonal. All the cross peaks identify its coupled partners. Similarly, if you go horizontally also, it identifies all its coupled partners. And I showed the advantage when there is an overlap, how COSY can be confusing and it can mislead the interpretation, whereas Toxy can easily circumvent that problem. Then we switched over to heteronuclear correlation. I showed you how heteronuclear correlation works. It is simple correlation of one spin, one proton, let's say proton to carbon, nitrogen, etc. to any other heteronuclei. So this is possible, and this pulse sequence is also heteronuclear correlation is very simple. In the case of proton, we allow it to evolve and do the inner polarization transfer, create a antiphase coherence for proton, then simultaneously apply 290-degree pulses on proton and carbon. Then the coherence jumps from proton to carbon and detect carbon. It is a very simple experiment. That is what we discussed. And then I showed the example of how we can interpret the carbon 13 HETCOR experiment. First of all, HETCOR is not symmetrical and there are no diagonal peaks. And usually in one dimension you will have indirect dimension, you will have a less abundant spin. Direct dimension is the abundant spin. In other way is also possible. And we took the example of one or two molecules and very easily we knew how to interpret the spectrum. So with this I will stop here and we will continue with the inverse experiments in the next class. Thank you.